All right, this is section 15.3, video 3. Now that we've kind of got the feel for this, let's see if we can move these along a little bit quicker. So something we haven't seen before is our domain here is x squared plus y squared equals 4. So that's a circle. We sketch that. You're talking about a circle with a radius of 2. So 2 here, -2, -2, and so on. So if we're going to do this as a type 1 region, which to me just seems like the easiest because I prefer to do type 1 if possible, it's going to be top to bottom, which means we need to solve this equation for y. Our domain equation needs to be solved for y. So that's going to be y squared equals 4 minus x squared, take the square root. Now don't forget this is very important. The plus or minus here is important because the positive part of that's the top half of the circle, where the negative of that is the bottom half of the circle. And then the x values are going to go from -2 to 2. So we pretty much have our double integral set. So it looks like we're going to have the double integral. So the x is on the outside from -2 to 2. The y is on the inside, so it's the negative square root of 4 minus x squared to the positive square root of 4 minus x squared, 2x minus y, again, dy dx because it's type 1. And it would not have mattered in this case because taking the antiderivative with respect to y or x first would not have created a problem. So let's go ahead and work this one out. So we're going to get the integral from -2 to 2 of, now let's take the antiderivative with respect to y first. 2xy minus 1/2 y squared from negative square root of 4 minus x squared to positive square root of 4 minus x squared dx. All right, let's see, plugging the square roots in, we're going to get 2x square root of 4 minus x squared minus 1/2. The square root of 4 minus x squared squared is just going to be the 4 minus x squared minus. Plugging in the negative square root, we're going to get minus 2x square root of 4 minus x squared, and then minus 1/2 4 minus x squared, because I'm squaring it again, remember, so the only good thing that I think is going to happen here is we're going to get a little bit of this to cancel out. It looks like this minus 1/2 4 minus x squared is going to cancel out the minus 1/2 4 minus x squared and the other one. The square root parts are not going to go away. So it looks like we're going to have the integral from -2 to 2. So it's going to be 2x squared of 4 minus x squared minus the negative of that. So we're really going to get 4x square root of 4 minus x squared dx. And from here, it's not horrible. It looks like it's just going to be a relatively easy u substitution. So u here is going to be 4 minus x squared. That's the composite piece. Du will be -2x dx. And dx is going to be du over -2x. So changing the bounds, let's see, plugging in -2 for x, I'm going to get 4 minus 4, so that's 0. Plugging in +2, I also happen to get 4 minus 4, which is 0, which is even better because now I don't really care what the integral was. It doesn't matter because my integral goes from 0 to 0, so that gives me a volume of 0. And you might ask yourself, well, how am I going to get a volume of 0 in here? So what more than likely is happening here, because I don't know what this is without graphing it, over this particular region, whatever this thing is, it's a plane of some kind, means that more than likely, well, not more than likely it is, the plane has an equal amount of volume above the xy plane as it does below the xy plane. In other words, the net volume is what we're getting out of this, because remember, what we're finding is the volume which is above the xy plane, but over our specific domain, that plane must cross through the xy plane, giving us volume above and below. So we're getting a net volume there of 0. And we're actually going to revisit a way of doing this particular type of problem that's a little bit easier and shorter than this one. All right, in number 6, we want to evaluate the region bounded by the planes x equals 0, y equals 0, and z equals 0. So that's all of your coordinate axes. And the plane x plus y plus z equals 1. So let's take a look at what that looks like. So x equals 0, y equals 0, z equals 0. Again, that's all of your coordinate axes. The plane x plus y plus z equals 1. If we were to sketch that within basically the first octant, because that's what the x equals 0, y equals 0, and z equals 0 is going to limit us to. Let's see, we're going to have an x-intercept of 1 when y and z are 0, a y-intercept of 1, and a z-intercept of 1. So it looks like the region that I'm talking about is going to be underneath of this and in here. Trying my best to sketch over what I did there. It's not going very well. So it's going to be within basically that tetrahedron. So you could do this as a type 1 or a type 2. It doesn't matter. I think I'm going to probably go with this as a type 1. So a couple things we need to do. First of all, because it's going to be a type 1, I'm going to go ahead and sketch my domain, because again, I always think this is probably the best thing to do if possible. So if I'm looking at this thing, basically what it looks like in the xy plane, it looks like this, that triangular region in your xy plane. And if I'm going to do it as a type 1, I'm going in that direction. So y will vary from a function to a function. So it looks like y is going to go from 0 up to that linear function right there. And that linear function is, well, let's see, that's 1, that's 1. So we know that the linear function here is going to be y equals 1 minus x, because it's going to start at 1 or have a y-intercept of 1 and a slope of negative 1. It's going down 1, right 1. So that's that equation right there. So y is going to go from 0 to 1 minus x. Y will vary from 0 to 1 minus x, and that's going to be our dy. X has to go from a constant to a constant. Well, that's pretty obviously going to go from 0 out to 1. All right, so the only other thing we need to do is this thing has to be solved for z, because it's got to be a function of x, y. So we just need to subtract x and subtract y on both sides. So we're going to get z equals 1 minus x minus y. So that's going to be what we're going to take the antiderivative of, 1 minus x minus y. All right. So let's go ahead and take the antiderivative with respect to y first. So we get y minus xy minus 1/2 y squared, evaluated from 0 to 1 minus x dx. Don't forget the integral 0 to 1. So before I take this antiderivative, I'm actually going to simplify this just a little bit first, because I know I'm doing this, I'm sorry, not antiderivative. Before I plug in the bounds here and use the fundamental theorem, I'm going to simplify something first. What I can see, and this is kind of one of those tricks, is what I have here is I have y in common in those first two terms. So what I'm going to do is I'm actually going to factor the y out, which leaves me with a 1 minus x. And then I've got minus 1/2 y squared. Why, might you ask, am I doing that? Well, take a look at what your bound is on top. Your top bound is a 1 minus x. So watch what happens here. This is kind of cool. So if I plug in 1 minus x for y into this y right here, I get 1 minus x times 1 minus x, which is 1 minus x squared. And then here I'm going to get minus 1/2 of plugging the 1 minus x into the y, I get 1 minus x squared. Plugging 0 into both of those makes them both 0, so that's kind of nice. That's gone. So this is what I'm left with to integrate. Well, I have a 1 minus x quantity squared minus half of a 1 minus x quantity squared, so that's really just a half of 1 minus x squared. This is actually going to be a much easier antiderivative to take. Pull the 1/2 out, oops. Pull the 1/2 out to the front. When I take the antiderivative of 1 minus x squared, you might want to do a little u substitution if you don't need to do the u substitution, because you remember the little trick that says that that's a linear composite piece. So I'm just going to take the antiderivative of the whole thing, which would be 1 minus x cubed. Dividing by the new power is 1/3, but I still have to remember to multiply by the reciprocal of the slope of the composite piece. The slope of the composite piece is -1, so I do have to have a negative on the outside there as well. Don't forget the extra 1/2, so I'll throw the negative way out in the front. And then we'll evaluate that from 0 to 1. Now, if all of that didn't make sense, do the u substitution. U would be 1 minus x, and then you would end up with the same thing. So you're going to get -1/6 of, plugging in a 1, I get 1 minus 1, which is 0. Plugging in a 0, I get 1 to the 3rd power, which is 1. So ultimately, I get -1/6 times -1, which is 1/6. And there we go. So kind of a nice trick there. When you have one of these tetrahedrons, this works out that way, that you're going to be able to do that little factoring thing, and you should be able to combine your inside terms. But again, that really works out when it's a tetrahedron like this. So kind of keep that in the back of your mind as a little shortcut that you can do. All right, find the volume bounded by the cylinder, x squared plus y squared equals 1, and the planes y equals z, x equals 0, z equals 0 in the first octant. The hardest part about this one is sketching it, trying to figure out what the heck is going on here. So I'm trying to find the volume bounded by the cylinder, x squared plus y squared equals 1. So that's a cylinder with a radius of 1 that basically surrounds the z-axis. So it's going to look something like this, up through here, and so on. Technically, it doesn't stop. Oh, yes, it does. I'm sorry. It says in the first octant, so I don't need to worry about extending the cylinder. The cylinder itself extends in both directions on the z-axis infinitely. The hard part is this plane, what this is going to look like. So let's see. Find the volume bounded by the cylinder and the plane y equals z, x equals 0, z equals 0. X equals 0 is going to be the yz plane, and z equals 0 is going to be the xy plane. So we are basically talking about, again, the first octant of this thing. The y equals z. So when y equals 1, z equals 1. So you're going to have a point, and this is very difficult to draw from this perspective. So when y equals 1, which is out here, z equals 1. So about right there. So it's going to cross through right about there. When y equals 0, z equals 0. So it's going to go through the bottom right there. I am not probably going to do this justice, but the plane is going to do something. You see, that was pretty horrible already. Let me try that again. Because I got to try and stay parallel here. Plane is going to do something like this at some kind of a weird angle. Again, this is really hard to do. You're going to end up getting this region which is sliced kind of like on this weird angle right here, going through there. I'm going to actually try to draw this as a separate section so that you can see it a little bit better than what I have drawn. All right, so I know that the base region is going to be part of this circle right here. X squared plus y squared equals 1. So the base region is going to look something like this. Again, when x equals, excuse me, when y equals 0, z equals 0. So I'm going to have a point right here. When y equals 1, z equals 1. So I'm going to have a point right there. So the side of this thing, because it's going to be up along the I'm drawing a blank here, the xz plane right there. Oh, sorry, the yz plane. And then it's going to actually, because it's cutting through the circle, and this is the hardest part, is it's going to come around. It's got to meet this point right here, because ultimately it's going to be flat up against the edge here. So what it's going to do is it's going to follow the curve and look something like that. So it kind of looks like a cheese wedge or something like that. I don't know what the best way to describe that would be. That's what it looks like to me anyway. It looks like a cheese wedge. So again, that's a very difficult one to kind of visualize and see. If you can use some kind of a graphing tool or something, a three-dimensional graphing tool to help you out with that one, that's probably not a bad idea. Think I'm probably going to want to do this one as a type 1, because I think that it's easy enough to do it either way in this case. So type 1 is going to go from there to there. So y is going to vary from function to function. X is going to vary from number to number. So let's see our type 1 region, just to make sure that we write this correctly. Type 1, our domain is going to be, x is going to go from 0 to 1. And I know that because it's a circle, or in this case, a quarter of a circle with a radius of 1. And then the y part is going to go from 0 to the top part of that circle. So I have to solve this equation right here for y. So y is going to be plus or minus square root of 1 minus x squared. Solving that. And I only have to worry about the plus part because it's the top half of that circle. So it's really going to go to the square root of 1 minus x squared. So there are my bounds. And again, please do not think that this is going to come extremely easy in the beginning. This stuff takes a long time to figure out sometimes. So take your time with it. So let's see. X is going to vary from 0 to 1. Y is going to vary from 0 to square root of 1 minus x squared. The function is y equals z, or z equals y. That's the plane that this thing is underneath of. So the function is literally just y. Remember, you solve it for z and plug that in. It's a type 1, so we go dy dx. All right, let's see what we get. Antiderivative with respect to y is 1/2 y squared from 0 to the square root of 1 minus x squared. Got your integral still with respect to dx on the outside. So let's see, it's going to be 1/2. Plugging in the square root squared is going to get rid of the square root. Plugging in 0 gives us nothing. So this should actually be a relatively easy antiderivative. From here, I'm going to pull the 1/2 out to the front. Antiderivative of 1 is x. Antiderivative of x squared is 1/3 x cubed from 0 to 1. Plugging in the 1 is going to give me 1 minus 1/3 on the inside of the parentheses. Plugging in the 0 gives me nothing. So it looks like I have 1/2 times 2/3, which is going to end up being 1/3. So the actual integration here was not the difficult part. The difficult part here was trying to figure out what this thing looks like and setting it up as the bounds. Again, it's not going to be the easiest thing to do to figure these things out, but I strongly suggest doing what you can to sketch them first and then figuring out whether you want to go type 1 or type 2. There will actually, again, be a slightly easier way to do a problem like this one. I think we're going to have to come back with a 4th video because we're already almost at 20 minutes. Only got 2 more examples. Should definitely not be as long.